every single time you ask an artificial intelligence to write a line of code, to generate a high-definition image, or to compile a complex medical diagnosis. A physical reaction occurs here on Earth, miles away from where you sit, inside a monolithic, windowless concrete warehouse. A bank of specialized silicon chips pulls hundreds of watts of power from a heavily strained municipal grid. Within milliseconds, these processors heat up to temperatures exceeding 80 degrees Celsius, demanding thousands of gallons of fresh water to be circulated through cooling towers just to keep the system from melting down. Our planet is rapidly running out of room, out of fresh water, and out of clean electricity to support this massive digital transformation. In January 2026, SpaceX made a quiet, yet world-shaking filing with the Federal Communications Commission. Their request was almost incomprehensible in its scale. They asked for permission to launch a mega constellation of up to 1 million satellites, designed specifically to deliver over 100 gigawatts of artificial intelligence compute power directly from low Earth orbit. Meanwhile, Google has quietly initiated its own high-stakes orbital project, known as Project Suncatcher, sending its state-of-the-art tensor processing units into the cosmos. This is no longer a far-off science fiction fantasy. This is the next great corporate gold rush. But this rapid migration to the heavens raises a vital and highly dramatic question. Why are the wealthiest technology companies on Earth preparing to build a trillion-dollar computer network in the harsh, highly irradiated vacuum of space when we have perfectly solid ground to build on? To understand how we reach this cosmic turning point, we have to look back at the history of digital storage. For decades, data centers were treated as the invisible, boring plumbing of the internet. They hosted our web domains, stored our corporate emails, and slowly backed up our family photos. They were built on cheap land near major metropolitan areas, plugged directly into standard municipal electrical grids, and cooled using basic, industrial-scale air conditioning. Because the flow of data was predictable, the physical footprint of these facilities grew at a manageable, linear pace. But then, the deep learning revolution arrived. Traditional cloud computing operates like a standard household light bulb, drawing power in a steady, highly predictable stream. Training a modern frontier artificial intelligence model, however, is closer to lighting an uncontrollable forest fire. The neural networks powering today's large language models require thousands of graphics processing units to be tightly clustered together in massive, multi-gigawatt server farms. On Earth, these clusters have hit a terminal physical bottleneck. According to latest reports from Bloomberg New Energy Finance, the capital expenditure of the 14 largest publicly owned data center operators is rapidly approaching an astronomical $750 billion. Over 23 gigawatts of data center IT capacity is actively under construction globally, with approximately 3/4 of that footprint being built inside the United States alone. This massive physical build-out is running directly into the limits of Earth's electrical infrastructure. In major technological hubs like Northern Virginia, Dublin, and Frankfurt, local utility companies are facing a harsh and unyielding reality. They simply cannot build new power plants or upgrade high-voltage transmission lines fast enough to feed these digital monsters. If a technology company wants to construct a new 1-gigawatt data center today, the waiting list to connect to the municipal power grid in heavily constrained markets can stretch up to 8 years. In a hyper-competitive technological arms race where being 3 months late to market can mean corporate obsolescence, an 8-year wait is a death sentence. Beyond the electrical grid lies an even more volatile crisis. Water scarcity. A single standard 40-megawatt terrestrial data center can consume over 1 million tons of fresh water every single year just to evaporate heat from its chips. In water-stressed regions across North America and Europe, local communities are starting to push back with intense anger. They are staging public protests and demanding that local governments pass strict zoning laws to deny data center permits, arguing that training algorithms should not take priority over human drinking water. The terrestrial model of computing is running out of environmental and social runway, and this is what has forced Silicon Valley to look up toward the stars. In the vacuum of space, the basic physics of energy harvesting undergo a radical and highly lucrative transformation. When solar energy travels toward Earth, Our thick atmosphere absorbs, scatters, and reflects up to 95% of the sun's raw power. In low Earth orbit, however, solar irradiance is approximately 36% higher because there is no atmosphere to get in the way. The real economic breakthrough lies in orbital mechanics. By placing a specialized computing satellite into a specific path, known as a dawn-dusk sun-synchronous orbit, the spacecraft can remain in a state of continuous, 24/7 exposure to the sun. It never experiences night, it never encounters clouds, and it is entirely immune to seasonal weather changes. Under these conditions, a single solar panel in orbit can produce up to 8 times more electricity than the exact same panel placed on the ground. To the financial officers managing these trillion-dollar tech budgets, this mathematical reality represents an irresistible business model. It means infinite, free, and completely clean energy, entirely divorced from the regulations, politics, and physical limitations of Earth's municipal power grids. The corporate battle for the ultimate high ground of computing is accelerating at a breathtaking pace. In late 2025, Google officially unveiled Project Suncatcher. By partnering with the satellite imaging specialists at Planet Labs, Google plans to launch its first pair of prototype satellites by early 2027. These experimental spacecraft are designed to test Google's custom Trillium version 6E tensor processing units against the absolute harshest conditions of low Earth orbit. Not to be outdone, SpaceX is leveraging its vertically integrated space empire. To build the millions of space-bound computers required for their grand vision, SpaceX is planning a massive 11 million square foot production facility in Bastrop, Texas called GigaSat, which will eventually feed into an even larger orbital assembly pipeline called TerraFab. By fully integrating the rocket launch, the satellite manufacturing, and the AI development under a single corporate umbrella, Elon Musk is attempting to build an unbeatable monopoly on space-based intelligence. At the same time, agile startups are beating the tech giants to the punch. Starcloud, an ambitious orbital infrastructure company heavily backed by NVIDIA, recently secured $170 million in funding, pushing its valuation to an impressive $1.1 billion. Starcloud successfully launched the first commercial NVIDIA H100 GPU into space and trained a functional machine learning model in orbit, proving that commercial off-the-shelf silicon could survive the initial launch and function in the void. Starcloud's leadership has made the audacious prediction that within the next decade, almost all new heavy compute infrastructure will be built off-planet. Yet, this gold rush in the heavens masks a series of deadly, cold engineering obstacles dictated by the absolute laws of thermodynamics. When we think of outer space, we think of extreme cold, given that the baseline temperature of the deep universe sits at approximately minus 270 degrees Celsius. But space is also an absolute vacuum, and in a vacuum, there is no air. On Earth, we cool high-performance silicon chips through conduction and convection. We run air or water over hot copper plates, allowing the physical molecules of the fluid to carry the heat away and disperse it into the environment. In the vacuum of space, there are no air molecules to carry that heat. The only way to cool a computer chip in orbit is through the highly inefficient process of thermal radiation, literally converting heat into infrared light waves and radiating them slowly into the empty void. This thermodynamic limitation creates a massive engineering paradox. To cool a single high-performance graphics processor, a satellite requires a giant, specialized radiator panel. To cool an entire cluster of chips, the size of these radiators must scale exponentially. Elon Musk's early designs for an orbital AI satellite feature solar arrays and thermal radiators spanning over 70 meters in width, making a single computing satellite wider than a Boeing 747 aircraft. The physical design of these orbital data centers is dictated not by the size of the processors, but by the massive, heavy cooling structures required to keep the silicon from melting into useless liquid metal. Beyond the cooling crisis lies the silent, destructive force of cosmic radiation. Outside of Earth's protective magnetosphere, high-energy protons and cosmic rays constantly slice through space. When these highly charged particles strike a silicon microchip, they can cause what engineers call single-event upsets. temporary digital glitches that flip binary bits from 0 to 1, corrupting complex calculations. In worst cases, they cause permanent physical damage to the delicate microscopic pathways of the processor. To prove that their hardware could survive this constant bombardment, Google had to place its Trillium TPU inside a medical proton accelerator, simulating 5 years of intense space radiation over a span of just a few weeks. While Google's engineers reported that the chips survived, the operational reality of space is unforgiving. You cannot send an IT technician to replace a broken server rack orbiting at 28,000 kilometers per hour. Because of this, orbital data centers are being designed under a completely different paradigm. Disposable infrastructure, continuous cosmic radiation, and microscopic thermal stress take a heavy toll. Engineers expect an annual hardware failure rate of roughly 9% in orbit. This means these satellites are built to run for a maximum of 5 years, slowly losing computing nodes over time, before they are systematically deorbited to burn up in Earth's atmosphere, only to be replaced by a newer, faster constellation. This disposable model, however, introduces a terrifying risk of orbital congestion. Launching up to 1 million active computing satellites into narrow orbital bands between 500 kilometers and 2,000 kilometers altitude increases the mathematical probability of the Kessler Syndrome. This is a catastrophic runaway chain reaction where a single collision between two satellites creates a massive cloud of high-speed debris, which then goes on to destroy every other spacecraft in its path. Such an event would not only wipe out the world's space-based computers, but could render low Earth orbit completely unusable for any human endeavor for generations to come. Furthermore, distributed artificial intelligence workloads require incredibly high bandwidth, low-latency communication networks. Training a giant neural network requires different chips to constantly talk to one another, swapping parameters in real time. On Earth, this is done via ultra-fast fiber optic cables. In space, Google is attempting to solve this by flying its satellites in extremely tight, hyper-coordinated formations of just a few kilometers apart, communicating via free space optical laser links designed to handle over 1.6 terabits per second of bidirectional data. If these satellites drift even a fraction of a millimeter out of alignment, the entire distributed computer instantly breaks down. Ultimately, do we truly need to put our data centers in space? The short answer is, not for every workload. The future of global computing will not be a complete replacement of Earth-based technology, but rather a highly calculated functional specialization. Terrestrial data centers will likely retain their absolute dominance over real-time, latency-sensitive applications. If you are hailing an autonomous rideshare vehicle, streaming a live broadcast, or processing a financial transaction, those computations must occur near your physical location on Earth to avoid the physical delay of beaming data to orbit and back. Space-based data centers will instead act as a massive, off-planet pressure valve. They are uniquely suited for asynchronous, energy-intensive batch workloads. Training the next generation of multi-trillion parameter foundation models, running massive scientific climate simulations, or processing continuous global surveillance data are tasks that do not require millisecond-level feedback loops. These workloads can be cleanly offloaded to the stars, soaking up the endless, unfiltered energy of our sun. Yet, as we gaze at this glittering future of orbital silicon, we must confront a deeply unsettling paradox. Are space data centers truly the ultimate savior of our digital world? Or are they a brilliant, highly dangerous distraction from the real crisis? Consider the environmental math. The primary justification for moving compute to orbit is to save Earth's strained ecosystems. But launching hundreds of thousands of heavy rockets to build, maintain, and constantly replace these disposable satellite constellations requires burning millions of tons of rocket propellant. The resulting emissions of black carbon soot, alumina particles, and nitrogen oxides directly into the highly sensitive upper stratosphere could inflict irreversible damage on our ozone layer. In our desperate attempt to protect Earth's local power grids and local water reservoirs, we risk poisoning the very atmosphere that shields all terrestrial life from deadly cosmic radiation. This brings us to the ultimate dilemma. Is the true solution to our insatiable appetite for artificial intelligence really to colonize the stars with burning computers? Or is it to fix how we compute here on Earth? After all, there are highly viable terrestrial alternatives that do not require the astronomical financial costs and catastrophic physical risks of orbit. Microsoft's famous Project Natick proved that submerging data centers in the deep, freezing oceans of our planet can eliminate fresh water consumption entirely while utilizing natural ocean currents for highly efficient passive cooling. In countries like Iceland and Norway, technology giants are already building massive server complexes powered by abundant, zero-emission geothermal and hydroelectric energy, using nothing but the naturally freezing Arctic air to keep their systems cold with almost zero ecological footprint. At the same time, a silent revolution in software engineering argues that the answer is not more physical hardware, but dramatically smarter software. Technologies like neuromorphic computing, which closely mimics the highly efficient electrical pathways of the human brain, and optical computing on earthbound silicon could soon allow us to train multi-trillion parameter neural networks using only a tiny fraction of the electrical energy we consume today. Are we choosing to build a highly fragile, dangerous, and incredibly expensive orbital infrastructure simply because it is easier for corporate monopolists to bypass local earthbound regulations? Rather than doing the hard work of building sustainable, highly efficient computer systems on the ground? The entire commercial viability of this historic transition hinges on a single, decisive economic moat: the absolute cost of launch. Currently, launching payload to low Earth orbit using traditional rocket systems sits at roughly $1,500 per kilogram. At this price point, orbital computing is a highly specialized luxury, reserved almost exclusively for sovereign intelligence agencies, military communications, and high-security government operations. However, Google's internal economic models suggest that if the cost to orbit drops to between $100 and $200 per kilogram, the financial math flips entirely. At that price, generating a unit of AI compute in space becomes significantly cheaper than buying wholesale electricity and paying for water permits on the ground. This is the ultimate prize that Elon Musk is chasing with SpaceX's fully reusable Starship platform. If Starship can achieve its target launch costs, the economics of computing will be rewritten forever. We find ourselves standing at a truly unprecedented crossroads in human history. To construct the digital minds of tomorrow, we are preparing to wrap our entire planet in a dense, glowing ring of burning silicon chips, capturing the raw power of our local star to fuel our virtual dreams. Will this grand migration to the heavens be the ultimate environmental breakthrough that saves Earth's ecosystems from being consumed by the digital age? Or will we look up in 50 years to find that we have transformed our pristine night sky into a chaotic, crowded graveyard of trillion-dollar space junk? What do you think? Is sending our data to the stars a stroke of absolute genius? Or is it a monument to human hubris?